Hello, everyone. Welcome to CS50 at Yale. I am Benedict Brown. I teach CS. I'm a lecturer in the computer science department, and I'm the instructor here at Yale for CS50. This is my third year doing it. And next, I'll be introducing also the rest of the team at Yale, and then also much of the team at Harvard who's down today. So I'm thrilled to have you all here. We've been looking at the numbers of shoppers in the class. It's up about 40% over last year. This is phenomenal. We're thrilled. We'd love to see those numbers stay. It means that we will need to add a few sections, but we have the capacity to do that. So we can absorb that increase, and we hope that it stays. We've been doing this now for several years, and it's been getting a little better each year, and that will continue. So we hope to have an awesome year for you. If you're a graduate student or a faculty member or spouse that's interested in auditing, we're happy to have all of you in the class. Everybody's welcome. Again, for the graduate students and professional students, you'll probably have to get me to sign a form. I will be available after class, either up here on the stage for a while or back in the lobby. To sign forms, I'll be here again next week. We'll have a little tutorial on how to take CS50 and be successful and have a good time. I'll be signing forms then, and it's cs50.yale.edu on our website. I will be posting office hours where I'll also be available for that. The last thing I'll mention before introducing Cody and our head TAs is that after the lecture, don't forget on your way out to get a piece of cake. So, our course manager this year is Cody Murphy. And I'm going to pass this off to him.
Hello. Hi, I'm Cody Murphy, and I've been teaching math and computer science for a couple years, although never to a room this large. Shout out to David. But yeah, this is my first year here with CS50. I'm really excited. I've been learning from the best with Benedict and David, and we have a super awesome team, and we have some of them here today. Would you mind coming up for us? All right. Let's pass it off.
Hi, I'm Max. I'm a senior in Pearson, CS major, and I'm really jealous of the position that you guys are in right now, because CS is great. Yay.
Hi, everybody. I'm Reese. I'm a junior in Poly Murray. I am super excited to work with you guys, and I'm really excited to learn CS with you all.
And I'm Ileana, also a junior in Poly Murray, CS major, and just to let you guys know, you can always reach us by email.
Oh, sorry. Yeah, let's bring up David to finish off our lecture here and start it. And sorry.
Thanks, Cody.
This is CS50, Yale University's Introduction to the Intellectual Enterprises of Computer Science and the Arts of Programming. All of that and so much more will make great sense before long. And I thought I'd mention that Benedict and I actually go way back. He and I were classmates at Harvard some 20 plus years ago. And we went through our archives, even though this was well before digital cameras, and found this one. I used to go over to Benedict's room, and I was friendly with some of his roommates as well. And if you can see here, this is a stack of some very cheap pizza in Cambridge, Massachusetts from Pizza Ring. It was so amazing that they would give you 2 pies at once in the same box for like $8. And if we enhance here, this is our own Professor Brown. So he and I go way back, and it's only fortuitous that we've now come full circle and are together now teaching this course here at Yale. So if you are leaning toward computer science, you might already have some comfort with the idea of being in a class like this, but odds are you don't. And in fact, if you're anything like me back in the day, I had no interest in or really appreciation of what computer science was back in my first year of college. And in fact, when I got to college, I really gravitated toward things I was more familiar with. At the time, I'd come off the heels of high school, and I really liked like a constitutional law class in high school, and I liked history and that sort of domain. And so I just kind of naturally gravitated when I got to Cambridge toward government, which was the closest concentration or major there in Cambridge. And I was still nonetheless kind of a geek as a kid. I certainly played with computers or computer games, but I never really took a genuine interest in it. And even my friends, ironically in retrospect, who did take computer science in high school, like I thought they were actually the geeks and didn't really see the appeal of like heads down at a computer monitor, typing away, door closed, fluorescent lights. It just didn't really make any sense to me or resonate. But I finally, sophomore year, got up the nerve to shop a course that was, and still is now, called CS50. It was being offered only at Harvard at the time. And even then, I only got up the nerve to go into that lecture hall because the professor at the time let me sign up pass-fail, since I really rather feared failure of some sort, because it was just so new and unfamiliar to me. But long story short, I ended up falling in love with it once I actually came to realize what it was. And no joke, on Friday evenings, when back then the homework assignments or problem sets would be released, like I would legitimately look forward to going back to my dorm room, 7 p.m., the P set would be released, and diving into that week's programming challenge. But why? So at the end of the day, computer science really isn't about programming. It's probably not about what you perceived your own friends as doing in high school versions thereof. It really is about problem solving more generally. So if you're feeling at all uncomfortable with the idea of shopping or taking a class like this, realize that most of the people around you feel that same way. 2/3 of CS50 students each year have no prior CS experience. So even though on occasion it might sound like it, perhaps based on answers that others seem to be giving or facial expressions they might be having, it's really not actually the case. 2/3 of you are feeling as uncomfortable or less comfortable as I was back in the day. But the course itself, as you'll see in the syllabus, really focuses on students individually. There is no course-wide curve per se, but rather what's going to matter ultimately is not so much where you end up relative to your classmates at the end of this course, but where you end up relative to yourself as of today, and focusing on that delta and that sense of progression yourselves. So what then is computer science, right? I dare say we can simplify it as this, so problem solving. Well, what does it mean to solve a problem? And that domain itself doesn't have to be engineering, doesn't have to be science per se. Really, I dare say we can generalize problem solving to be a picture like this, right? There's some kind of input, the problem that you want to solve, and there's an output, hopefully the solution to that problem. And then between is the sort of proverbial black box, the sort of secret sauce that somehow takes that input and produces that output, and it's not yet apparent to us how it does that, but that's the goal ultimately of computer science and solving problems more generally. But to get to that point, I claim that we need to talk a little bit about what a computer scientist would call representation, like how you actually represent those inputs and those outputs. And odds are, even if you really aren't a computer person yourself, you probably know that computers only speak a certain language of sorts, an alphabet called binary, so binary, but probably fewer of you have an appreciation of what that actually means and how you get from zeros and ones to Google Documents and Facebook and Instagram and applications and all of the complexities that we use and carry around with us every day. But let's start with the simplest form of representation of information. Like if I were to start taking attendance in this room, I might old school style just take a piece of chalk or a pencil and just say, OK, 1, 2, 3, 4. And then I might get a little efficient and say 5, just to make obvious that it's a 5. but these are just hash marks on the screen. And of course, I don't have to do it in chalk. I can just do 1, 2, 3, 4, 5, and then count even higher if I use other digits as well. And digits is kind of a nice coincidence there, and we'll come back to that in just a moment. This system of using hash marks on the board or using your own human fingers is what's called unary. Uno implying 1, where the hash mark is either there or it's not. And so 1, 2, 3, 4, 5, it's like using sticks or fingers or hash marks. That's unary notation. There's only one letter in your alphabet, so to speak, and it happens to be a 1 or a hash mark or a finger, whatever the unit of measure happens to be. So you can get, though, from using that unary notation, of course, counting up even higher if we use more hash marks or more fingers. And we get to the more familiar system that we all use, which is called the decimal system. Dec meaning 10. And the only reason for that is because you've got 10 letters in your alphabet, so to speak, 0 through 9, 10 total digits. And these are the kinds of numbers that you and I use and sort of take for granted every day. But a bunch of you already know and realize that computers somehow only speak zeros and ones, and yet, my God, a computer, my phone, any number of electronic devices these days are so much more powerful, it would seem, than us humans. So how is it that using just zeros and ones, they can achieve that kind of complexity? Well, it turns out it's pretty much the same way we humans think. It's just we haven't thought this way explicitly for quite some time. For instance, on the screen here is what? Shout out the obvious. 123, right? But why is that? 123. Well, really, all that's on the screen is like 3 symbols. And frankly, if we rewound quite a few years in your development, it would look like just 3 cryptic symbols. But you and I ascribe meaning to these symbols now. But why? And from where does this meaning come? Well, if you roll back far enough in time, odds are you'll recall that when thinking about a number like a pattern like 1, 2, 3, we sort of instantly these days intuitively ascribe meaning. So this is the so-called ones column or ones place. This is the tens column or tens place. And this is the hundreds column or hundreds place. And so all of us rather instantaneously these days do the math 100 times 1 plus 10 times 2 plus 1 times 3, which is, of course, 100 plus 20 plus 3, which gets us back, to be fair, to the same symbols. But now they have meaning because we have imposed meaning based on the positions of those values and which symbols they are. So all of us do this every day anytime we stare at or use a number. Well, it turns out that computers are actually doing fundamentally the same thing. They just tend to do it using fewer letters in their alphabet. They don't have 2s and 3s, let alone 8s and 9s. They only have 0s and 1s. But it still works because instead of using these values, for instance, I can go ahead and use not 0 through 9, but just 0 as 1 as follows. Let me give myself sort of 3 placeholders again, 3 columns, if you will. But rather than call this 1, 10, 100, which if you think about it are powers of 10. 10 to the 0 is 1. 10 to the 1 is 10. 10 to the 2 is 100. We'll use powers of 2. So 2 to the 0 is going to give us 1 again. 2 to the 1 is going to give us 2 this time. And 2 to the 2, or 2 squared, is going to give us 4. And if we kept going, it'd be 8, 16, 32, 64, instead of 1,000, 10,000, 100,000, a million, and so forth. So same idea, just a different base system, so to speak. Indeed, we're using now binary because we have 2 letters in our alphabet, 0 and 1, hence the bi prefix there. So in binary, suppose that you use, for instance, these digits here, these symbols, 0, 0, 0. What number is the computer storing if it's somehow thinking of 0, 0, 0, but in binary, not decimal? Yeah, it's just 0. The decimal number you and I know is 0. Why? Well, the super quick math is, well, this is just 4 times 0 is 0, plus 2 times 0 is 0, plus 1 times 0 is 0. So that gets us back, of course, to 0. But in the computer, if it were instead storing a pattern of symbols that isn't 0, 0, 0, but maybe 0, 0, 1, you can probably imagine that now, just do the quick math, this is now the decimal number we know as 1, because it's 4 times 0, 2 times 0, but 1 times 1. Skipping ahead, you might be inclined now to represent the next number here as what? It's obviously not 002 because we don't have access to the digit 2. We only have 0s and 1s. So you might be inclined to do something like this, 1, 1, right? Because if I'm counting to 2 on my fingers, it's 1, 2. So 2 hash marks on the board would seem to give me 2, but not in binary. This is unary. What do I get in binary with the pattern 0, 1, 1? Yeah, so it's actually 3. So the correct way of counting up from 0 on up in binary would be to start as we did, 0, 0, 0. Then we go up to 0, 0, 1. Then we go up to 0, 1, 0. Now we go up to 0, 1, 1. And anyone, how do you count to 4? What's the pattern of symbols then? Yeah, 1, 0, 0. Now, skipping ahead, if we wanted to represent not 4, but rather this value, how high up can we go with just 3 columns? 7, right? So 4 plus 2 plus 1 gives you 7. So if you wanted to represent 8, what happens next? Yeah, so you sort of carry the 1. So just like in our human world, when you go from 9 to 10, you typically carry the 1 to a new column over to the left. Exact same idea. So the number 8 in binary, so to speak, would now be this, but you need a 4th column, just like you would in our human decimal world. So what then is the mapping between these low-level ideas to like actual physical computers? Well, inside of computers today, whether it's your Mac or PC or your iPhone, your Android phone, are millions of things called transistors, which are tiny little switches that just turn on and off. If you've ever heard of a CPU, the central processing unit, that's the brain of the computer, or the phone these days, that just has so many of these microscopic switches that can turn things on and off. What are they doing? They're really just storing or not storing electricity. After all, what's the only thing you and I do probably at the end of the day, or even in the middle of the day, if we want to keep using our devices? Well, we plug them into the wall, or we plug it into a battery. So there's some low-level flow of electrons, or however that works. But generally speaking, the only physical input to your phone or your computer these days is like an electrical socket or some battery in the wall or elsewhere. And that's kind of an interesting principle, because if the only input you have is there's either electricity flowing in the form of electrons or whatnot, or there's no electricity flowing, like the battery is dead or the plug isn't plugged in, well, that gives you 2 total states in the world, 2 different conditions that your device can be in. It's either plugged in or not. It's either drawing power or it's not. And what's perfect about binary is that you have 2 digits, 0 and 1. That's all we have in the physical world when it comes to charging some physical device. So there's this really nice mapping between 0s and 1s and electricity or no electricity, or turning something on and turning something off. So for instance, if we use a very large transistor like this physical phone, I might say I have 1 switch on this phone. And indeed, I can now turn it on like this. So my phone, this physical device or switch, might now be representing the number we know as 1. And if I go ahead and turn it off, it's now representing, of course, 0. And if I grabbed a couple of more phones and sort of held them like this, you could imagine that each of these phones, or in turn switches, is just representing a column and a value. So if you give me 2 phones, I can count from 0, 0 to 0, 1 to 1, 0 to 1, 1. And that's 3 total. So with 2 phones or 2 switches, I can count as high as 3. If you want me to count higher to like 7, I'm going to need a 3rd phone or a 3rd switch. Or an 8, I'm going to need a 4th phone or a 4th switch. So this is what all of those transistors or switches inside of your computer are being used for, to store information. So once you have that ability to store information, you can start to represent anything that's familiar. Right? With just 0s and 1s, switches that are on and off, you can represent these numbers that we think of as binary now, but you can map them, so to speak, to decimal, like the number 7 or the number 8. So how in the world, if all a phone or a computer has is electricity and these switches and this ability to think in binary, how do you get to like letters of the alphabet? How do you send a text message? How do you write a document, which of course involve alphabetical letters, not just numbers? Like, what's the leap we now need to make? Well, we'll leverage what's called in computer science this notion of abstraction, right? We're not going to spend any more time in this class talking about electricity. That's sort of a very low-level detail, so to speak. In fact, we might rarely talk about binary, which conceptually is sort of one level higher in your mind now than the electricity that flows from the wall, right? Who cares how the electricity works or flows? I just know that I can turn something on or off. From that, I can get binary. But if I only have binary, I can only represent numbers. Now I want letters. So we need to now take things up a notch, so to speak, and start to use these same ingredients to represent things like the letter A. So how, whether you know this or not coming in the door, how, given only those inputs to the problem, might we think now about representing the letter A in a computer if all of we have is binary, or in turn switches, or in turn electricity? What do you think? Using 8 bits, so that's in the right direction indeed. I'll probably want more than just 3 or 4 columns. And indeed, you use the right term here. If you've ever heard the expression bits, that just stands for binary digit condensed into one word. And so these indeed represent bits, a 0 and 1. OK, so yeah, we're going to need a few more bits. But how do we get to like the letter A? How do we build up conceptually? How about in back? Yeah, that's literally all we can do. All we have is the ability to store numbers. We humans just need to decide, you know what? In the context of a text message or the context of Google Docs or Microsoft Word, you know what? When you see a certain pattern of bits, don't display it as a number. Display it as a letter instead. So we might go super simple and say A is 1, and B is 2, and C is 3, and so forth. Well, humans decided not to use quite that mapping years ago. It turns out that the capital letter A in your phone or computer is actually stored using the number 65 in decimal. So the pattern of bits that gives you the number 65 is what your phone or computer is storing if you want to represent the number 65. And humans came up with mappings for B and C and D and other letters as well, and they called this mapping ASCII, the American Standard Code for Information Interchange. Not interesting what the acronym stands for, but that it's indeed exactly as you described, a mapping between numbers and letters. So if we take this a little further, here's where the mapping goes thereafter. B is 66, it turns out. C is 67, and so forth. And so if right now you were to receive a message from a friend that happened to be implemented using zeros and ones, and those zeros and ones that you just received wirelessly somehow were representing the numbers, say, how about 72, 73, 33, what message did your friend just send you? If they sent you 72, 73, or 33. I think hi, and then that's HI. What might the third one be? Yeah, you would only guess this unless you knew it coming in. It's indeed an exclamation point, because HI is 72, 73, exclamation point. If we actually looked beyond the dot, dot, dot on my slide, we would see that 33 is among those values. And indeed, that is how a computer represents an exclamation point. You receive, either via a wire from your desktop computer or wirelessly on your phone or laptop, a pattern of zeros and ones that represents the number 33 in this case. And underneath the hood, really then, is just some pattern of bits. It might be represented using light bulbs, sort of old school style. It might be represented using hash marks on the screen or zeros and ones that you might draw. We can all just agree that there's probably a way to represent zeros and ones by just turning things on and off. Now we can kind of think at a higher level of abstraction from the electricity down here, binary here, and now this thing called ASCII, which is sort of one level conceptually above it. And indeed, that's where we get this notion of abstraction. You have a low-level detail that, frankly, is not really all that interesting to a lot of us. Who cares how electricity works? Just care that it does work. But if you stipulate that it does, now you can represent decimal numbers, and then we can all agree to have some mapping, as you propose, to letters as well. So two fundamental ideas so far, representation and abstraction, that give us the more familiar. But what about any of the other symbols that we all use, right? American Standard Code for Information Interchange is itself a little biased toward American English. And indeed, that's what happened early on. There were only 128 and then eventually 256 possible characters that you could represent in a computer, which was generally biased to A's through Z, capital and uppercase, some numbers, and some punctuation as well. But there's a lot more symbols in other languages that aren't represented on a typical keyboard. For instance, any accented character in Asian languages having a whole symbology as well. There's a lot more characters in the world than 128 or 256 certainly. So how do we get there? Well, the world came up with, indeed, yet other characters that you're familiar with as well, not to mention all of these guys, which you probably use pretty incessantly these days. Those are just characters on the keyboard. They don't look like letters in any language. They look like little comical characters. These emoji are actually just a mapping from numbers to letters as well. And that is thanks to something called Unicode. So years after ASCII was decided by a whole bunch of folks decades ago, Unicode was developed to not use a total, as you proposed, 8 bits, but Unicode allows you to use maybe 16 bits or 24 bits or even 32 bits, which means the more columns you have, the way bigger numbers you can represent, because you keep having more and more and more columns or places. So Unicode allows you way more than the original value. So for instance, as of this year, we double checked, this is the most popular emoji still in use to this day. This is the face with tears of joy. They all have names as well. Anyone want to hazard a guess as to what number this is? It's not 65, it's not 66, not 72, 73, 33. We've seen those. 100 higher. 1,000 higher. So a billion's too high. It is 128,514. Completely arbitrary, but we humans, unbeknownst to us, have agreed that this number shall be displayed as a picture of a smiling face that's smiling so much that it has tears of joy in its eyes. And every other emoji you've ever sent similarly has a mapping as well. But if you really want to take the fun out of emojis, next time you send an emoji to a friend, this is literally what you're sending to your friend. Some esoteric pattern of zeros and ones that their phone is just displaying in a more interesting way, using a font of sorts to interpret those bits. All right, so that was a whirlwind tour so far from electricity on up to emojis. Any questions so far? Yeah? Mm. Really good question. So in simplest form, if you go way back into time when you had those old big monitors called CRT or cathode ray tubes, where you could actually see the dots composing the letters on the screen. If you have a childhood calculator, that's kind of similar. The little LEDs show you really the physical representation of those values. When you don't have fonts, everything is just fixed width. Like someone built a piece of hardware that will display the first character here, the next character here, and so forth. And typewriters in yesteryear did exactly that. There was no proportionality. There was no kerning, so to speak, between characters. But once you have fancier Macs and PCs and phones these days, were born the notion of fonts. And Apple, years ago, really spearheaded this especially. So there are other zeros and ones in any Word document or any Google document that you use that are storing other patterns of bits that essentially tell the Mac or PC or phone what font to use to display those characters. And these days, and we'll talk about this actually in just one moment, your screen is just this amazing canvas of like millions of dots called pixels. And these fonts can sort of use those pixels in different way, and sometimes they'll be more squished, sometimes they'll be wider, but it's more zeros and ones, and humans just needed to decide at Apple and Microsoft and elsewhere what patterns of bits represent Times New Roman or Comic Sans or some other such fonts as well. All right, so suffice it to say that in a smiley face, like tears with face with tears of joy, there's a lot of yellow dots, or it would seem, or just yellow color. And indeed, that dot is generally known as a pixel. Well, a pixel is sort of another thing that, well, the computer's got to represent it somehow. After all, how does the computer know to show me yellow or green or blue or anything else? Well, it all reduces to pixels as well. You might have heard this acronym in some context in the past. RGB stands for red, green, blue. And if you hadn't heard that before, that's no big deal. It just describes a common convention for computers to store any color of the rainbow. They break down every color you can think of into some amount of red, some amount of green, some amount of blue, that if you overlap those three shades, you get the color that you want, for instance, something like yellow. So for instance, if we consider this picture here, this is 3 pixels side by side, or really RGB, a triple, if you will, 3 different values of sorts. So red comes first, green comes second, and blue comes next. So really underneath the hood, suppose that your computer were storing the same numbers as before, 72, 73, 33, but now it's in the context of Photoshop or a browser or some program that's designed to show graphics and not text. Well, the computer will interpret potentially that same pattern of zeros and ones in just a different way. Rather than display them as text, like hi, H-I exclamation point, it'll display it as the combination of these 3 colors. So you'll take some amount of red, some amount of green, some amount of blue, and it looks like a good amount of red, a good amount of green, and less blue, just based on those numbers, 72, 73, and then less, 33. And if you actually combine those with each other, what you'll ultimately get is, if we merge them together, that same shade of yellow. Now, so let me stipulate for the moment that each of those values of red and green and blue, by human convention, tend to use 8 bits. So with 8 bits, anyone want to guess how high you can count if you have 8 columns on the board? Yeah, you have to do some quick math, but if you literally are 1, 2, 3, 4, 5, 6, 7, 8, this is the 1's place, this is the 2's place, the 4's place, and so forth. If you do out that math, you can count as high as 255 using 8 total bits or 8 total columns. This is a very common unit of measure, and it's one of those things eventually that'll just become second nature because it's used in so many places. And indeed, it's used in colors. The computers of today typically use 8 bits, 8 zeros and ones, to represent how much red you want for every dot on the screen. 8 more bits to represent how much green you want on the screen. 8 more bits to represent how much blue. So they spend 24 bits total to represent how much red, how much green, how much blue each dot on your screen should be, and then display the resulting value as it might be here with this yellow dot. But the only thing that's changed is the context in which those bits are interpreted. Not a word processing program, but like a graphics program, it still reduces to zeros and ones. And you can see these pixels or dots, right? This is that same emoji as before. And if I start to zoom in on this, you start to notice a pattern. And indeed, that like lovely shade of yellow and the black eyes and so forth are actually just a whole bunch of dots that when you look at it normally, they're so small you don't realize that it's a very jagged image. But if you zoom in on it quite a bit, you actually start to see the pixels on the screen. And you can kind of do this, not so much with phones these days. If you've ever heard of retina displays and the fancy things that Android phones and iPhones have, your human eyes can't really even see the dots anymore. But if you go home to your TV or look at an older TV especially and get way too close to be comfortable watching it, you'll actually see these same dots as well. And that just means every one of the yellow or black or gray dots on the screen is being represented by this Mac or PC using 24 bits. So the top left-hand corner, that's 24 bits. The next dot over is 24 more bits, 24 more bits, and so forth. So if now you've ever taken a photo and you've stored the file like a JPEG on your computer, and it takes up 1 megabyte. 1 megabyte means 1 million bits, and 1 million bytes. And a byte, anyone know? It's just 8 bits, right? 1 bit is pretty useless, right? You can only count to 1. But 8 bits, you can count, we just said, to 255. So most people in the world talk about bytes. 1 megabyte just means 1 million bytes. So that's a lot more zeros and ones. So once you have a file on your hard drive storing an image, the bigger the photo is, the bigger the file is going to be. Or the higher the resolution is. The more dots your photos have, the bigger the file is going to be. Why? Well, because for every one of those dots, if we, at the risk of oversimplifying, you have to store another 24 bits, 24 bits, 24 bits, 24 bits, and so forth. So the bigger the image, the more disk space it's going to take up, and the fewer files you can even store, therefore, on your Mac or PC. This is why, ultimately, you run out of space. Now, I borrowed this from online. We'll see if it sort of remains a thing this year as well. But you might have noticed quite a few GIFs, graphical interchange formats being posted to this Facebook and certainly many others online. You might have noticed that some of those graphics are sometimes animated. They literally say GIF, and if you click on it, something sort of happens. And sometimes you can upload videos, certainly, to sites like Facebook as well, and hit a play icon, and then that plays as well. Well, how does that fit into this sort of hierarchy? Well, again, we started with electricity, zeros and ones. Then we had letters. But instead, if you don't interpret those zeros and ones as letters, but sort of conceptually think about them now as colors, you have images. That's all an image is, a bunch of dots or pixels. Well, what is an animated GIF? If you've ever seen some meme going around where it's sort of an animation, it's just image, 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 and sometimes it loops. Image, 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 and it creates the illusion of motion. If you were a kid and ever had one of those flip books with like hundreds of pages of like cartoon drawings, and you flip it really fast, that's just creating the illusion of a video by showing you lots of frames per second. And that's all a video is. Once we agree that, yeah, I can store images because it's just a bunch of pixels, each of which is interpreted left to right as red, green, blue, how much color I want for each dot, well, then all you need to do is store more of those pixels to represent the second frame of a movie, the third frame of a movie. And in our human world in Hollywood, most movies are 24 frames per second or 30 frames per second. That just means when you're watching a video or even an animated GIF, you're watching dozens of images fly by your eyes every second, creating the illusion, therefore, of motion. And that's all a video file is. And so here, too, we can take the fun out of clicking on any of the memes online because you're just looking at bits and bits and bits flying across the screen in some pattern. Musically as well. If any of you have ever played a tune on a keyboard or some other device, well, we could think about how we can represent sounds as well, right? These are musical notes, so to speak, and each of those notes might be played on, for instance, a piano for some unit of time, so maybe 1 second per note or much faster than that. So you could imagine maybe storing with zeros and ones the note you want to represent, maybe A or B or C or D, E, F, G, the amount of time that you want to play that note for. Maybe it's a split second, maybe it's a quarter of a second, maybe it's a full second or the like. And if you really want to get fancy, we can maybe store a third value. How loud do you want that note to be at some moment in time? And if you just imagine now these triples, note and note and duration and volume, and just keep doing note, duration, volume, note, duration, volume. Now you have a whole musical staff that can be played audially so long as you have speakers as well. So it's just using these bits in different patterns and in different ways. So that's how we might represent inputs and outputs. When you save a file in Microsoft Word or Adobe Photoshop, you're creating an output by saving these patterns of zeros and ones to your computer's, say, hard drive. All right, so that gives us inputs and outputs. But what's inside of the so-called black box? This really is where computer science now comes into play. These are things called algorithms. And in your own understanding now, what is an algorithm, if you could? What's an algorithm? Let me go a little farther back. Yeah, and back. An instruction to do something, presumably. Other perspectives? An algorithm's an instruction. Something else? Yeah. A path to follow. So a logical path to follow. Yeah, and let me combine those two. It's really like step-by-step instructions for, shall we say, solving a problem. That's all an algorithm is. And so when you hear about algorithms and machine learning and artificial intelligence, which use algorithms, those are just step-by-step instructions that computers are using to solve some problem. So that's, I claim, what would be inside of this black box in the middle. So what might a sample algorithm be? Well, one that you saw an allusion to a little bit ago is this old school device here, so a phone book. And inside of a phone book are hundreds or thousands of names and numbers, typically alphabetical from A to Z. And even though this is old school and most of us don't even use these anymore, frankly, it's the same thing in our Android phones and iPhones. Those just happen to be digitally implemented, but they're still sorted A to Z, top to bottom. And so instead of flipping through pages one at a time or two at a time, now we're just kind of scrolling through one at a time. But of course, on our phones, you can search for things, and you can type in a friend's name and try to look them up in your phone. Well, back in the day, you would do that similar in spirit, but you would have to do it with your own human eyes and not software. But how is software implementing that same step-by-step approach? Well, if I want to find someone like Mike Smith in this phone book, last name Smith starting with S, well, I could certainly just start at the beginning and look on the first page, and nope, he's not there. Second page, nope, he's not there. Nope, he's not there. One page at a time. That is a step-by-step process, an algorithm. Is it correct? Yeah, it's correct in the sense that if Mike is in here, I will find him if he is. Is it good algorithm? No, I mean, it's pretty stupid. This is going to take me forever to go one page at a time. So right in grade school, I could do things twice as fast by going 2, 4, 6, 8, 10, 12, and it's actually easier said than done, and so forth, and fly through the phone book twice as fast. Is that algorithm correct? No, why? What's the catch? Yeah, I could skip him accidentally, right? Once I get pretty deep into the phone book, I just might get unlucky, and he happens to be sandwiched in between two of the pages that I'm flying through. So there's still a fix. I don't have to just never use two things at a time. I can just make sure that when I hit SN in the phone book, or maybe the T section, I know I have to at least double back maybe one page. So I can fix that bug or mistake, as it would be called in programming, and then see if he's on that page. But most of us, if we're going to use this technology at all, are not going to search 1 or 2 pages at a time. What's a normal person going to do? Sorry? Just open it. OK, I am in the M section. I don't see Mike. Keep going where? To the S, like just more pages. OK, so more pages, but direction matters. So I probably want to go to like this way to the S's if I'm ending up in the middle in the M's. But what does that mean? It means that I know Mike is not in any of this half of the phone book. So both figuratively and literally, we can tear the problem in half. Tear the problem in half, and now I'm left not with 1 byte or 2 bytes out of the problem as my first algorithm's involved. Now I've taken like 500 bytes out of the problem all at once, but they're not incorrect, right? I know Mike, as you say, is not there because he's toward the S's. All right, what do I do now? I open it up. All right, slightly too far. I'm in the T section now. What do I obviously do next? Now he's this way, but that means there are like 250 pages that I know he's not on. So again, my algorithm of 1 and 2 at a time is completely blown away by this much faster algorithm as well. And I can repeat, and I can repeat and repeat. And if I get it right, hopefully I'm going to end up with, eventually, if we fast forward, 1 page, and Mike Smith is either on the phone books page or he's not, and I can go ahead and call him then. So this is just intuitive, and frankly, that's exactly what your phones are doing when you search for a friend. It happens in a split second. But your phone, typically, if you're looking for Smith in your phone, it's not searching from top to bottom among your contacts. It's jumping mathematically to whatever the middle is, and that's probably M, give or take, depending on the distribution of your friends' last names. And then it's going to jump forward or back without you seeing this as a human, finding that value. And what's the takeaway there? Well, just how much more efficient was this? Well, the first algorithm, how many steps might it take me in a 1,000-page phone book to find Mike Smith? Yeah, I don't know, like 700, 800, something like that, like hundreds of pages. All right, what about the twosies approach, 2 pages at a time? Like 350, 400 pages, right? Half as many pages because I'm flying through twice as fast. How many times is it going to take me to look for Mike Smith using the third algorithm where I kept dividing the problem in half and dividing and conquering, if you will? And it started with 1,000 pages. 3, more than 3, unless I get lucky. It's closer to 8, 9, 10, right? Because 1,000 can you be in half is 500, then 250, then 125, then I have to round, and then I keep going. But I can do that 10-ish times, depending on the precise number of pages. 9 or 10 times will get me to one final page. So that means I started with 1,000 pages at first. I can, in 10 steps, your phone can, in 10 steps, find that friend in the phone book if they are actually there. The first 2 algorithms would have taken 700 steps, 350 steps, or at worst, the whole phone book if I just keep going and don't find him. The algorithm that we had more intuitively is indeed the same. And without getting too mathematical, we can actually appreciate this even graphically. So if here's sort of a very simple chart. On the x-axis or horizontal is the size of the problem, like how many pages are in your phone book. The vertical axis on the left is how much time does it take you to solve the problem. Seconds, page turns, whatever your unit of measure is. Well, the first algorithm I can draw like this. It's a straight line. The slope has a 1-to-1 ratio, because if Verizon or the phone company next year adds 1 more page to the phone book, that might push Mike 1 more page forward. So that might take me 1 more unit of time to find him. So a 1/1 slope. The second algorithm is also a straight line. It's just lower than the red line, because for any given number of pages on the x-axis, wherever I want to put my hand, I'm going to hit the yellow line at some point, and that's how many page turns or seconds it takes. But if I go higher up, twice as high up, then I'll see how much time the first algorithm took, the red line, because it's working half as fast. But the third algorithm is what we'll call this curved green line. It's a different shape. And even if it's you hazy memories as to what the term means, it's what we call at some point in your mathematical backgrounds logarithmic. And if you haven't, we'll see it this term, not to worry if it's unfamiliar altogether. But this has a fundamentally different shape, It's not a straight line. It's curved. And notice that it almost kind of sort of gets flat even. It never becomes flat. It just grows or rises ever so slowly as you go farther and farther out. Why? Well, think about it from another perspective. If Verizon doubles the number of people in the phone book next year, maybe 2 towns, East Haven and New Haven, merge together into one bigger phone book with twice as many pages, well, how many more steps will it take you to find Mike Smith next year in that case? Like 1 more step. Like that's a really powerful idea. Just to go up 1 second or 1 page turn on the vertical axis, you have to go way, way out on the x-axis, which again represents the number of pages. And that's a powerful algorithm. And what I claim is that even if you're feeling uneasy with the idea of computer science, let alone programming, a lot of the ideas we're going to explore this semester really are as familiar as that. And it's really just a process of translating those ideas and that human intuition you already have into what we'll call code. And what a perfect then setup to actually introduce some code, but not in a specific programming language. So we'll begin with this, pseudocode. So pseudocode is not a formal language. There's no one way to write it, and every one of us on the staff might write the following algorithm in a slightly different way. You just use English-like syntax and grammar, or whatever your spoken language is, to convey your ideas. So for instance, to implement that algorithm that I ended on, finding Mike Smith, by dividing and conquering again and again, how would I express that a little more methodically, in such a way that another person or ultimately a computer could understand? Well, I might jot down that step 1 is just pick up the phone book. That's where I began. Step 2 would be open to the middle of the phone book. You know, give or take. I can be a little sloppy about it even if I want in the human world, and it'll average out in the end. Step 3, look at the names, looking for Mike Smith on the current page. It's the M section, so I already know he's not going to be there. So then I have to ask myself a question, though. If Smith is among the names, what do I probably want to do? Call him or do something with that information. So I'll indent that underneath to make clear that there's cause and effect here. If step 4 is true, then I should do step 5. That's all the indentation means. But if Mike is not on the page I'm looking at, which he's not going to be if it's the M section, then I might ask, well, else if Smith is earlier in the book to the left, then what do I want to do? Well, as you proposed, go to the left of the book, and in this case, open to middle of left of book. And if I then don't find that he's earlier in the book, but rather, then I have to go back to line 3. Why? Well, let's be clear. If on line 6, Smith is earlier in the book, he's to the left. Based on where I'm in the book, what do I want to do? I want to open to the middle of the left half of the book and then go back to step 3, because the next step should be look at the names if I've just jumped elsewhere in the book. And I can repeat the same process again and again without writing this down to be 20 or 30 or 40 lines. I can reuse some of my own syntax to be more efficient. But if Mike is later in the book, I instead want to open to the middle of the right half of the book and then, again, go back to step 3, because I want to see if he's on now that page to the right. Now, I'm not quite done. Mike's either there, or he's to the left, or to the right, or there's one fourth case, so to speak. He's not there, and I should consider this. So if I want to make sure, I should say else. If he doesn't fall into any of those 3 scenarios, I should just quit. And if we fast forward a bit, among the delights in any programming class ultimately is your first of many bugs or mistakes that you might make. And you've seen bugs before in the world of Macs and PCs and even phones. If you've ever seen an annoying little spinning beach ball on Mac OS, or you've seen the little hourglass thing spin endlessly on Windows, or if your iPhone or Android phone just freezes altogether, very likely the human who wrote the code that your phone or laptop are running at that moment just didn't anticipate some 4th or some 5th possible scenario, and therefore there was no line of code that the computer could use to handle that scenario, so it just crashes or spins forever or reboots or does something unexpected. So even something like this, if you left out this condition, you might be looking for Mike endlessly spinning beach ball if you never actually tell yourself to quit or to exit. So we'll see more evidence of that before long. But let's apply some now programming terms to these ideas here. So highlighted in yellow now are henceforth what we're going to call functions. These are just actions or verbs that tell the computer or the human or the robot what to do in pseudocode here. So those are all verbs or actions. Here, we have what we're going to call conditions or branches. These are like decision points or metaphorical forks in the road. You're either going to go this way or that way, just like in the phone book, or maybe a 3rd or 4th direction as well. But how do you decide what road to go down logically? These are a little more fancily called Boolean expressions, after a mathematician named Boole in yesteryear. And a Boolean expression is just a question that has a yes/no answer, or a true/false answer, or, if you will, a 1-0 answer. We could reduce that to bits as well. Lastly, we'll have these things highlighted here, which we're going to call loops. And going back to line 3 is indeed inducing this kind of idea. Go back and do something again, such that you're in some kind of cycle, or as we'll say, a loop. And those are 4 of the ideas in programming that we'll see now in actual code, and 4 of the ideas that will persist throughout the whole semester. These relatively simple building blocks that you and I use every day, either intuitively or maybe even on paper, are just ways of breaking down problems into step-by-step instructions, or, again, algorithms. But we're going to add a few things to the list in just a moment. Things called variables, which you might recall from algebra or math more generally. Things called threads, which are a little more specific to computing. And events, which we'll see especially later in the semester. But we're going to do this as playfully as we can by way of this character here named Scratch. And odds are some of you probably used in high school, middle school, grade school. Yes, a few? So Scratch is this amazing language from MIT's Media Lab, developed some years ago. And indeed, it's targeted primarily at younger students. But it actually encapsulates all of these ideas that we've discussed thus far. And we use it in CS50 as a springboard in the first week to our second week, wherein next week we'll introduce you to a language, or week and a half about, we'll introduce you to a more text-based language, more traditional language called C. But let's see if we can't see, no pun intended, let's see if we can't see some of these same ideas latent in some of the code here as well. So I'm going to go to a website here, scratch.mit.edu. And ultimately, in a week and a half, when the first problem set or programming assignment for the course is due, we'll provide you with all of the step-by-step instructions to do the same thing yourself. The first thing you can do, as you'll see in the homework, is to create something in Scratch. And you'll be prompted first to create a username and password so that you have somewhere to save your file. But I'm just going to do my things here on the fly. And by default, we'll see an environment that looks like this. And I'm going to go ahead and dismiss the default tutorial just to give a definition of what's here on the screen. So on the left-hand side here is a whole bunch of seeming puzzle pieces, little colorful blocks that in just a moment I'm going to drag and drop and interlock them like an actual puzzle. In the middle here is what we'll just call the programming area. This is the editor, where I'm going to drag and drop those puzzle pieces. And over here is what MIT calls the stage. It is the area of the screen where Scratch, the default cat that we see, can move up, down, left, right, make sounds, or do any number of other things. So we're going to create code by dragging and dropping those puzzle pieces into the middle. And then when I click the start button effectively, well, things start to happen. So perhaps the very first thing or simplest thing I can do with Scratch is this. Notice how on the left-hand side here, there's these colorful categories that just group different ideas into different types of puzzle pieces or blocks. The first one up here under events is where I want to begin. The event, the act of clicking a start button on a phone or a laptop is what a computer scientist calls an event. It's something that happens that the computer can listen for. And we'll see now that there's this little green flag, like in a game, that when clicked over here at top right will just start the code running based on whatever I've typed. Now, the only thing I want to do is make Scratch look a little different. And if I scroll over to looks over here in purple, there's a whole bunch of puzzle pieces, one of which is just say hello by default. So I'm going to go ahead and drag and drop that puzzle piece next. And notice that as I get close to an existing puzzle piece, they're sort of magnetic and they want to interlock. So if I just let go, they now snap together. And one of the very first programs written years ago historically had just this phrase here, hello world. Some of the very first few words ever spoken in a computer program. So we'll repeat that legacy here. So I now have a program. It's super simple. It's only got 2 puzzle pieces. But how do I go ahead and play it? Well, the code is telling me what to do. When the green flag is clicked, go ahead and say hello world. So that is a program, right? There's no text, there's no C++, there's no Java, there's no Swift or any languages that you might generally have heard of thus far. Scratch itself is a language that happens to be graphical, but it has these same ideas that we'll see in fancier forms soon. In fact, what has just happened? Let me go back for just a moment here over to where we began. And you'll recall we had this definition of problem solving. Inputs passed into algorithms, which yields outputs. Well, let me propose that we consider the input in this particular program just to be this, hello world, the words I happen to type into that little ovular box. Then the algorithm is just to say something. Like that is the code that's taking as input those words. And what is the output going to be? Well, hopefully, if the code works, it's going to make the cat say with a little speech bubble, hello world. That's the output. So this super simple program already fits into this paradigm. Well, what if I want to do something a little more interesting? Let me go over here now, and let me go ahead and let's see. What else can I have Scratch do for me here? It looks like there's a whole bunch of movement that I can do. It looks like there's a whole bunch of looks I can give him with saying something. Looks like there's sound capability. Let me scroll down here to sensing, for instance. Oh, no, this one's interesting. Ask what's your name and wait. So I can maybe make this program more interactive so that I have to do something beyond just click a green flag. Well, let me go ahead and get rid of this for just a moment. And to get rid of a block, you can just take it to the left and let go, and it disappears. Let me drag this one in here, and I'm fine with that. Ask what's your name and wait. And notice over here, this puzzle piece is a little special. It comes with a sort of special dependent piece, the answer that the human has typed into their keyboard. So how do I go ahead and use this? Well, let me go back to looks up here. Let me go ahead and say something for 2 seconds. And what do I want to say here? Let me go ahead and say hello, comma. And then let me go back to sensing to get this thing. Oh, no, sorry. Let me go ahead and get one more puzzle piece. Say something else for 2 seconds. But notice this. I don't have to say anything there per se. I can instead go to this answer. And even though it doesn't quite look like it'll fit, these blocks will grow to fill. And indeed, it feels like it's magnetic. Now I can say hello, comma, and then say so-and-so's name. So let's try this. Let me go ahead now and click the red stop sign. Now the green flag. What's your name? I'll go ahead and type in David and hit enter. Hello, comma, David. I mean, kind of underwhelming and kind of stupid aesthetically. Why? Like, what rubs you the wrong way? It's like 2 seconds. Hello, David. Like, I just want to see it all in one breath, if you will. But I can't type in words and then drag that puzzle piece there because it's going to overwrite or fill the white oval. So what can I do? Well, if you start to poke around, and this is a lot of what programming is initially, just reading the documentation or Googling for definitions of functions that exist you haven't heard of yet, or just skimming a list like this, well, I'm going to go down here and scroll further. Well, this is a little weird for a default example, join apple and banana, but those are just sample words that you can plug in. So you know what I'm going to do? I'm going to grab this answer, and I'm going to get rid of the second say block, because I really just want one thing to happen. And you know what? I'm going to change apple to hello, comma, and I'm going to change banana to answer. And joining is going to do what's more fancily called a concatenate, combine two things left and right. And then let me go ahead and drag this. It's going to magnetically snap into place. And now I think we have the right idea. What's your name? Let me try it again. David. Hello, comma, David. But notice how we're sort of building up almost vertically on the program by nesting and nesting and kind of stacking these puzzle pieces. But that's OK. And notice here what's happening. So this puzzle piece here, ask, is somehow asking the user for input and then returning it in some sense, handing it back in a variable, as we'll call it, called answer. So in computer science and programming, we don't call variables x, y, z typically. We give them actual names that are more descriptive, like answer. So here is a variable storing an answer, and we can now use that here. Well, what is join? Join is another function, an action or verb that's going to join two inputs together and create one new output, like hello, comma, David. That output can become some other function's input, hence the stacking that I'm doing. So hello, comma, David is what's actually passed into the say function. And that's why I see my name ultimately printed. So if we break this down into the same paradigm as before, if we start with problem solving as before, the input initially to the ask block is what's your name, and the algorithm in question is, of course, ask. The output of that is whatever the human's answer was, stored in this thing called a variable, just by scratch for me automatically. Well, then, if I consider the second line of code, there's two inputs, and that's OK. You don't have to pass in just one input. You can pass in 0 or 1 or 2 or more. Hello, comma, and answer are my two inputs to this process. The algorithm now is going to be that join function. And it's going to figure out how to combine these two things left and right. The output is hopefully going to be hello, comma, David. But now that output, if we shift it over, can become the input to some other algorithm or function. And that function here might be say. And that hopefully is going to output hello, comma, David, right out of the cat's mouth. So again, problem solving is reduced to different forms based on the language you're using. And at the moment, the language we're using is indeed this language called Scratch that allows us to program, literally, by just dragging and dropping puzzle pieces. Any questions, then, on these steps thus far? No? All right, well, let's try something a little fancier. How about this? Instead of when the green flag is clicked, let's actually make the cat do something a little more interesting, like play sound meow until it's done. OK, adorable. Didn't take much effort, but an adorable program. But if I want it to meow again, I can do click the green flag. Click the green flag. This is not the most interactive. Well, it's actually very interactive. It's not the most automated program, like if you have to play the game again every time you want to hear the cat meow. So what kind of programming construct or idea can we use from before to automate this? Yeah, so some kind of loop. So if I kind of poke around in Scratch, indeed under Control in orange, there's a couple of looping blocks. Repeat some number of times, 10 by default, but I can change that. Or forever. I can make the cat meow forever if I do something like this. Let me grab the forever block. And I don't want to put it here. I want to logically kind of break this up and reconstitute it. Let me put it in here. And again, that gap will grow to fill the block. Now let me connect it to the green flag so that now, I mean, it's not a very happy cat, perhaps. So maybe I should grab this. And notice, this is all very interactive. Let me wait 1 second after playing the sound. Now it's a little less worrisome what the cat is doing. And so we now have a program that's actually using a loop. Well, we can use loops in other ways. Let me go ahead and open up something that let's have the cat, for instance, count up here. So how about this? Let me get rid of this. Let me undo this. And let me go ahead and grab a variable. And it turns out you don't have to just use the answer that we got from the ask block. That variable you just kind of get automatically for free in Scratch. You can make your own. So I'm going to actually create a variable here. And I'm going to call it counter. And sure, I'm going to click OK. Notice, it gave me now a new orange puzzle piece called counter that I can now use somewhere. So it also gave me these other orange puzzle pieces like set counter to 0. And that's what I want to do. I want to write a program now that in a loop just counts upward. So to do this, I'm going to grab that and set the counter to equal to 0. Then forever, I'm going to go ahead and, you know what, I'm going to say the value of that counter. So I'm going to drag this in here. 2 seconds is going to take too long, so let's just change it to 1 second. Now I'm going to go back to my variable category. And I'm just going to drag this one in here, just as I did before with like, hello, my name. And then, sure, I'll go ahead and wait 1 second just to slow things down. And then I'm going to go back to variables. And again, I'm doing this quickly only because I've kind of tinkered with this before. I'm going to change the counter by 1. So notice I've made a fancier program. But logically, it's just going to set the counter to 0. And then it's forever going to say the counter's value. Wait a second. Change the counter by 1, then do it again, and again, and again, and again. There won't be any sound this time, but we will see that Scratch in this way can count, it would seem, from 0 on up to infinity, theoretically. But we'll see that infinity, things tend to break as you approach infinity in most programs. But more on that before long. Well, let me go ahead and open a few that I brought with me here. In fact, on the course's website, you'll see for every lecture, whether here or online, all of the materials that we use. And what I'm doing is writing source code, programming code. And if I click on Studio here, I'll actually see all of the code that I brought with me today. And I'm going to go ahead and open up an example now called PET. What about a program now that synthesizes those two ideas, using sound in a loop, but also using that loop to do something again and again? Well, let me go ahead and see what happens here. I'm going to go ahead and see inside, and you can actually see the code in question. And now watch this. I've clicked the green flag, but nothing seems to be happening. What should I do? And I clearly wrote this program already. Yeah, I should put the mouse over the cat, it seems. Why? Because it says, forever, ask the following question. If you're touching mouse pointer, then play the sound meow until done. So let's try that. Here we go. Oh, so now it's like, now it is more interactive, and you're sort of petting the cat with your cursor. OK. But if you hold it there, it gets a little annoyed. Let me go ahead and open a slightly different one, PET1. Notice I'm starting to count at 0, just as I did here, just because that's a computer science convention to start counting at 0. So PET1 is now my second example. Let me go ahead and see inside this one. It's a little more involved. What should I perhaps not do this time? And it's a little small. Let me zoom in. All right, so now logically, it seems clear that I shouldn't, for instance, do that. So don't pet the cat in that particular case. But again, notice all we're doing, even though the programs are getting a little more fancy and a little more involved, I'm just composing more advanced algorithms using all of these individual building blocks. We can make a really adorable cat, for instance, do this. Let me go ahead and repeat the following forever. Let me go ahead and find the motion block. And I'm going to go ahead and point towards the mouse pointer, my cursor. And then I'm going to go ahead and use this one, move 10 steps. But I'm going to do it one step at a time. A step is like dots on the screen, pixels. So one step means one dot at a time instead of 10. Let me play this. And now we have sort of a cat that follows me. But I'm much faster than him. And so I could, for instance, stop this, have him work faster, and do 10 times as many things. And now he'll actually follow my cursor until he gets there. And now this is kind of a bug or my mistake, right? Like he's apparently going just past my cursor, so then he's doubling back, but then he's gone just too far, so he's doubling back. So this is a bug, and it's because I'm taking 10 steps at a time. It's kind of jumping over my cursor in this case here. Well, let's go ahead and make something a little more involved. Let me go ahead and open this one, bounce 0. So I'm going to go ahead and open this one just as you can do later. Bounce 0 takes that same idea, but automates it this time. So this is kind of interesting because it's now responding to its environment. And if I zoom in there, notice that it's still the same movement idea, but it's not following my cursor. But it is asking the question, if you're touching the edge, a Boolean expression, turn yourself around 180 degrees. Now we can do something kind of interesting there. Notice that in Scratch, and now this has less academic value, has this ability to play with sounds. And if I go in here, for instance, and add sound, whoops, not search for sound, and I go ahead and record sound and allow my microphone to be used, again, ouch. OK, that's what the word ouch looks like, apparently, in a computer. And now let me go ahead and go back to code. And now if I go to sound, you'll see play sound meow until done. That's fine. But what I actually want to do is play sound recording 1. That was the default name I just gave it. So now, ouch. 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 OK, so we can do even more than that there. But you know what? This looks a little silly. So, sound aside, ouch. He's not really, ouch, walking. Ouch, right? He's not really walking. He's just kind of sliding across the screen. But you know what? What is just walking? Well, walking is really just animation. And if this is what the cat looks like by default, what if I use some graphic artistry and just kind of give him another look, another costume, as Scratch calls it? And now I'm in slides. I'm just going to go back and forth, left and right. First, second, first, second. And if I do this, now it kind of looks like he's walking. This is like a really bad flip book. Like every page he just moves like halfway toward his step. But that's really all animation is tricking our human eyes into thinking that something's happening in real time when really you're just seeing photographs fly by your eyes. But I can go ahead and do this. So in fact, if I go into bounce 1, I did this in advance already here. And this one's just a little fancier, such that now he's really moving, right? And if you really want to see it, we can move just 5 steps at a time. Actually, let's do whoops, not 51. 1 step at a time. And he's moving slower, but now it's changing costume a little too fast. So it's only once we kind of find the sweet spot, maybe 50 steps. OK, now a little too fast. But this is all animation is. Whether you're doing it in software or manually or flipbook style, you just have this ability to create now the notion of motion. But there's some other features too. We've seen variables, as I mentioned before, but it turns out we can take advantage of fancier techniques in programming as well, like in this sea lion here. So this one's interesting because this is the first Scratch program for which I kind of have to scroll to see 2 different algorithms, both of which are going to run when the green flag is clicked. And we won't get into the weeds of the code. All the code is online, and for the first problem set, you'll be able to take a closer look. But notice what happens with this program. He just barks endlessly in a loop because, notice this, there's this forever block down here. This is annoying. And if you can read the code, how can I stop him from barking? Yeah, there seems to be the space bar. If key space is pressed, set a variable called muted to true, or rather, check if muted is true, and if so, change it to false, else set it to true. So if I hit the space bar, now he stops. But I haven't stopped the program. If I hit the space bar again, he's still going. But what I'm doing is I'm changing a variable called muted to true or false, to 1 or 0. And then up above in my code, I'm actually checking here. If muted is false, then play the sea lion sound. So if it's not muted, go ahead and play the sound. So it's a way of creating your own questions that you yourself can answer ultimately so that you can finally have more interactivity. And speaking of interactivity too, if you ever played the game Marco Polo in like a pool as a kid, for instance, it's this game where one person, one kid like covers his or her eyes, and then they yell out Marco, and I look like an idiot right now, don't I? And then everyone else yells out Polo, and you try to find the other person in an otherwise dark space or pool space with your eyes closed. So if I go ahead and play this now, notice what? If I hit the space bar now, the orange puppet says Marco, and then the blue puppet says Polo. Now, it's not hard to implement that in code with just one single script, as Scratch calls it. But notice that each sprite here can have its own scripts. This is the orange Muppet scripts. This is the blue one's scripts as well. So notice that what the orange guy is doing is this. If the key space is pressed, say Marco for 2 seconds, but other sprites, other characters can't just look on the screen for what's happening. They have to be communicated with more programmatically. So there's this notion in computer science called events. This puppet can broadcast an event, which is like a secret message that only computers can hear. And the blue puppet, notice, can be listening for that event. And he can respond not when the green flag is clicked, but to a different event when he receives this event from someone else. So you can have multiple characters on your screen somehow intercommunicating in this way as well. And lastly, let's go ahead and take a look at this here. I'm going to go ahead and open up an example of coughing. So kind of a simple example. And this example of coughing just has a sprite doing something like this. Cough, cough, cough. It works. It's correct if my goal is to cough 3 times, but it's poorly designed, right? Like even knowing what we know already, you can kind of imagine doing this better using what? Yeah, so using a loop. So in fact, in cough 1, which is a newer version of this, it's the same idea. Let me see inside. Let me hit play. It does the same thing, but notice that I'm using the repeat block. So not forever, because I don't want to cough 3 times. Forever would be bad, probably. But 3 times seems reasonable, but I can do it now in a loop. But notice that if you wanted to now use this notion of coughing in like another program you write, it's a little annoying that you would just kind of copy-paste these puzzle pieces again and again and again anywhere in your program where you want to make a character cough. But what Scratch provides us with is actually this capability as well. At the very bottom of Scratch is this pink piece for make block. You can make your own functions. You can make reusable puzzle pieces that you can then use in different places. And so for instance, if I want to make a puzzle piece that coughs so that I don't have to construct it from scratch like that, no pun intended, notice what I can do here. I can literally in Scratch, and this may be something you use for your own problem set, define a new pink piece called cough, or whatever you want, attach some puzzle pieces below it, like say cough for a second, then wait for 1 second, and then you can use that puzzle piece in your own code, sort of out of sight, out of mind. Now I can program like this. So a moment ago, there was like 5 or 6 puzzle pieces. Now it's been whittled down to 3 by making my own puzzle piece cough that takes its own input and produces its own output. And suffice it to say, you can have your own functions, your own pink puzzle pieces that take 1 input or 2 inputs, not just 0 inputs in this case. And it's a way of modularizing your code ultimately and making it ever more usable. So that was a lot of little demonstrations, but it's worth kind of bringing this all together. Ultimately, in problem set 0, the challenge ahead is going to make anything of interest to you, whether it's a game, an interactive animation, or artistic work, all implemented in Scratch. And we thought we'd share with you the project from a former student here called IB's Hardest Game, not to intimidate, but we'd need, in closing, just one brave volunteer who would be comfortable playing one of your predecessor's homework assignments in front of a few people and on the internet. Hi, Bar. Yeah, OK, right there in the green, is it? Yeah, come on down. What's her name? Uwem? OK, come on down. All right, yes. Encouragement. OK. OK, sorry, your name again was? Uwem. David, nice to meet you. Come on around. I'm going to go ahead and full screen the game. We won't actually look inside. And I'm going to go ahead and click the green flag. And you're just going to use the keyboard, ultimately, to play this game. OK, and if we could raise the volume a little bit, Brian. All right. All you.
You can't touch this. You can't touch this.
Let me move this cursor over. All right. So you'll notice now, I'll explain the pedagogy, ultimately, of what you're now doing here. So what is the Yale symbol? Now it's wearing a costume that's not a cat. It's instead the Y, Yale logo. There's a second sprite, MC Hammer at the end, who's the one he's trying to touch with the other sprite. There's now 2 more crimson sprites, Harvard logos, each of which has its own puzzle pieces, all operating when the green flag started. Very good. OK. And notice, OM's not able to go past the black walls. OK, here comes MIT. You'll notice the MIT sprite is a little smarter. Artificial intelligence, if you will. Nice. OK. The walls are now gone, so there's no if touching edge, then bounce anymore. Nice. Nice. 2 of them. Notice they are clearly pointing toward him. Nice. Oh! Hang in there. Class might run a minute or 2 late. Nice. Second to last level. Yes. All right. Whoa. Dartmouth got you. Hang in there. A few more lives. Oh, hang in there. Yes. Yes. OK, one more try. One more try.
Break it down.
All right. All right. Big round of applause for OM nonetheless. There you go. Thank you. Allow us to conclude in our final moments with a look now of what else awaits with the course. Just as in Cambridge now, is there a tradition here in New Haven of a whole series of events, the first of which is CS50 Puzzle Day in just a weekend or so, the second of which is the CS50 Hackathon, an opportunity with all of your classmates up at Harvard, if you'd like, to join us from 7 p.m. to 7 a.m. working on your final projects, and ultimately the CS50 Fair, a campus-wide exhibition here at Yale of all of your final projects. So even if you've never programmed before, here is what awaits you in the next weeks of class. That's it for CS50. Cake is now served.